today. So my thesis today is ultra-efficient universal SHA-2 and BLAKE accelerators for decentralized networks. So before exploring my architectures and accelerators, so let we go to the very first, is the background. So I guess a lot of you know about Bitcoin because Bitcoin is the most popular cryptocurrency today. But today we won't talk about Bitcoin, we just talk about the technology behind Bitcoin, which is blockchain. So blockchain has several advantages like high security, immutability, and availability and trust. So to achieve these advantages, the blockchain network is secured by hash function. So the most famous one is SHA-2 and BLAKE. So let me explain a little bit about SHA-2 and BLAKE algorithms. So SHA-2 and BLAKE algorithms are the process of compressing message input to the hash output, and it can be reversed this process. So this is the list of SHA-2 and BLAKE functions. Like SHA-2 algorithm have several sub-functions like SHA-2 224, SHA-256, SHA-284, SHA-112, and similar to the BLAKE algorithm. So the next one, let me show you the SHA-2 and BLAKE applications. So the SHA-2 and BLAKE algorithm is aimed to apply for Society 5.0, which is the super smart society. So in the Society 5.0, we have two spaces. The first is the cyberspace, and second is the physical space. So actually, the SHA-2 and BLAKE algorithm is applied for also both spaces. So in first one, cyberspace need blockchain for data security, but blockchain need the SHA-256, which is the sub-function of SHA-2, and also BLAKE 256 and BLAKE 512, which is also the sub-function of the BLAKE algorithm. And the next one, physical space. So the IoT devices here, they need hash function for data integrity. This is the reason that the SHA-2 function is needed here. So because SHA-2 is the most famous one and it's also the standard, this is the reason that a lot of IoT devices try to use SHA-2, and BLAKE is just a very new function. It's just only support for the blockchain right now. So this is the reason that the ultra-efficient SHA-2 and BLAKE accelerator are needed for the Society 5.0. So let we go to the next part, is try to elaborate the main use of SHA-2 and BLAKE. As you see here is the two groups in the SHA-2 algorithm. It can apply for normal application in the IoT devices like data integrity, HMR, or RFID, etc. It's also applied in the shared cyberspace for the blockchain mining. So as you see that, because they have to use a lot of SHA-2 sub-functions for all applications, these need high flexibility and high efficiency SHA-2 accelerator. And the next one, the BLAKE algorithm is just meant for the blockchain mining. The reason is BLAKE is more compact and better security than the SHA-2. This is the reason that design the high performance and energy efficient BLAKE accelerator is needed. So just summarize. So depend on application. Depend on the size of application. We can choose better architecture for the hash function. As you can see here, SHA-2 is for many applications. This is the reason that they need high flexible. But in this case, they just apply for the blockchain. Is the reason that they just only for high performance and energy efficient. Now, let's go to the first accelerator. So I guess a lot of sensei here know about this accelerator because I just presented 20 days ago in a colloquium B, so I just briefly presented about it. So first about SHA-2, I have some problems to tackle and goal. I divided some previous works into two groups. Group 1 is FPGA-based work and Group 2 is CPU or GPU. So in Group 1, they have several advantages like low power consumption and small area, but they have to trade off the low performance and also low flexibility because they just support for single SHA-2 function, and we will explain it more later in the next part. And in the CPU, they have several advantages like high flexibility and also like high performance because they have a lot of cores and threads. But they have trade-off for massive power consumption and large area. As you can see here in two groups, there's no flexible, high performance and energy efficient SHA-2 accelerator has been proposed yet. It means that there's no accelerator can contain several advantages in two groups like that. So to solve this problem, my thesis today is proposed new accelerator to achieve high flexibility and high throughput and also high hardware efficiency. Now, before going to my architecture, let's look about the previous work. So it depends on the characteristic, depends on the architecture, and I will divide it into four groups. So in the Group 1 is single SHA-2 56 or SHA-512 core. So even SHA-2 56 or 512 core, they use the 32-bit ALU or 64-bit ALU. So because this is just a compact and small ALU, they can achieve low energy, but they have to trade off the high latency. This is the reason that they achieve low performance. And moreover, they just support for single SHA function, like just only support for SHA-256 or SHA-512. This is the reason that they have no flexibility and low performance. And the next one is our Blockchain Accelerator in our group. As the Blockchain Accelerator has proposed by the multi-core architecture, is the reason that they can achieve high performance, but also have the problem is they only support for single SHA function. This is the reason that they have no flexibility. And the second one is the Programmable Accelerator. So this is the Emacs, which is also the accelerator of this is hardware architecture from the Nakashima Sensei groups. As you know, that it also has a high flexibility because they can they can be programmable and can be configured for any function, any computation. But they support better for machine learning. This is the reason that when I implement it when I implement the hash function, it just achieve very low throughput. This is the reason that this architecture has low performance. So in the final one, the CPU or GPU, they have high flexibility, as I mentioned about that, and also high performance because they have a lot of cores and threads, but they have to consume a lot of power consumption. This is the reason that they have low energy efficiency. So to go back to my proposed architecture in the first accelerator. So to be to achieve these goals, I have to propose three new ideas. So the first one is the multi-core processing element. Now, as you can see here, this is my overview architecture of the proposed Multimode SHA-2 accelerator at the system-on-chip level. So the ideal one is located in the Multimode SHA-2, the Multimode processing element here. As you can see here in the figure 2, I just want to highlight that the processing element used two ALUs. So why I have to use 2 ALUs instead of 1? So that I use 2 ALUs to improve the flexibility, as you can see here. So the multimode processing element can be configured to be parallel 32-bit ALUs to compute for SHA-256, or they can cling together to become one 64-bit ALU to compute for SHA-512, or they can link together to become the SHA-256 for the blockchain mining. This is the reason that they can support for various SHA-2 functions, and also the processing element array can configure for the short message computation or also long message computation. This is the reason that they have high flexibility. And the next one is the idea 2. I am to improve the performance and hardware efficiency. As you can see here, I just mentioned about the dual-ALU, ALU1 and ALU2. So in one ALU, they have a lot of operators, like 80 operators at one loop. This is the reason that we have to binet it to make it low critical path. By use binet, I can balance the workload. This is the reason that I can optimize the critical path and also improve the throughput and high performance. And anyway, in this architecture, we can compute for 3 messages in parallel. This is the reason that our accelerator can achieve high hardware efficiency. In the final one, in the next one, I want to improve for the blockchain mining, because our accelerator is also used for blockchain mining. So the idea 3 is named Nonce generator and detector mechanisms. So as you can see here, this is the double SHA-2 with Thesis architecture for blockchain mining. This is the block header and the nonce value. They have to try nonce value to find out the hash output smaller than target. But this is not an easy work. You have to compute for billion value of nonce to find out the valid nonce. It takes a lot of time. So the reason that we have to propose the nonce generator mechanism. As you see here in the architecture at the system on chip level, the bandwidth here it has the H bus here it has the limited bandwidth. This is the reason that when transfer a lot of information message input, they will achieve low performance. This is the reason that we have to propose the nonce generator mechanism to automatically generate input data. They don't need to wait for CPU to send data. And also the nonce detector mechanism used to detect the hash output. This means that this can automatically verify the output data. You don't need to use the CPU to check output data. Now, to better understand our proposal, as you can see here, this nonce generator and detector used to improve the performance. As you can see here, this is the detailed timing chart of proposed accelerator with and without the idea 2, idea 3. And see here, this is the accelerator without idea 3. They have a limited performance. The reason is they have to wait for CPU to transfer data to the accelerator. But in this case, they just only here they just only wait for the CPU send for one message input, and they can automatically increase the data or take the data. So this is the reason that they can achieve maximize the performance. So next one, this is our implementation to verify our accelerator on the real FPGA. This is our architecture on the Abel FPGA. this is the system on chip design on the on the FPGA using Vivado tool. So in the next part is very important part. Let we evaluate each idea one by one. So we evaluate the idea one first. So as I mentioned about the idea one, it just improves the flexibility. As you can see here, I'm just this is the power and throughput of 7 accelerator versions with 7 different processing element array. As you can see, at each different processing element array, they can compute for various SHA function and achieve like that. And as you can see here, in this case, this is the best for our accelerator. So the next one, I will evaluate the idea 2. The idea 2 is aimed to improve the dual-ALU. This is the reason that we try to compare the dual-ALU architecture with related work on FPGA-based work. So on the 2 FPGA, our throughput is 1.5 to nearly 40% or 40 times better in throughput, and also 1.4 to 6.9 times better in error efficiency. And the next one, I will evaluate the idea 3, which is the Nonce generator or Nonce detector by evaluate the the accelerator with and without the idea 3. As you can see here, with the idea 3, our accelerator can 4 times better in throughput and energy efficiency. So in the next one, let we compare to the related work at the system on chip level. It means that we have to compare with the previous work, implement the shortcut on the real devices. As you can see here, our accelerator can achieve better flexibility because they can compute for various SHA-2 functions, and also they are 7.8 to 59 times better in throughput, and also 1.3 to 5.8 times better in error and energy efficiency. And the final one, I will compare to the most powerful CPU or GPU. So as you see that our accelerator is 9.4 to 36 times better in power consumption, and also at least 29 times better in energy efficiency. So for fair comparison in this task, I use the open source in the internet. They just implement for better throughput for CPU or GPU. And the next one is the high performance and energy efficient BLAKE accelerator. So similar to the SHA-2, I also analyze problems to tackle and first of all, we also group it into 2 groups, classify it into 2 groups, like FPGA-based work and CPU or GPU. In the FPGA-based work, they have some advantages like low power and error, but disadvantages like they have low performance. And in CPU or GPU, we also know that they have high performance, but they have to trade off the massive power consumption. As you can see here, there's no high performance and also energy efficient BLAKE accelerator has been proposed. Please, the accelerator can contain for 2 advantages in 2 groups. This is the reason that in this thesis we try to propose the second accelerator, which is achieve high throughput and also energy efficiency. Now, before I go to my architecture, let we analyze the previous works. So depends on the architecture, and also depends on the characteristic. I also classify them into 3 groups. And group 1 is route transformation like core. As you can see here, they also propose the ALU to compute the BLAKE function. This is also very small and compact ALU. This is the reason that they can achieve low energy. But in this ALU, they have to require many loops, several loops. This is the reason that they have to trade off the high latency and achieve low performance. And the next one is the programmable BLAKE processor. They also have high energy because they just only contain for the ALU or some kind of very small module. But I have to require a lot of cycles by because the CPU have to transfer a lot of instructions to this processor for controlling the BLAKE computation. This is the reason that they have trade off the high latency and also low performance, similar to the first one. And the second one is CPU or GPU, similar to the SHA-2. They can achieve the high performance, but they have consume a lot of power consumption. This is the reason that they have low energy efficiency. Now let's go to our accelerator. How to design the accelerator achieve high performance and also energy efficient. Now in IU1, this is not just only very main contribution. It's just a small contribution. This is the fully BLAKE accelerator. In this architecture, we try to improve the performance and hardware efficiency. As you can see here, this is the overview architecture of fully BLAKE accelerator. So with this architecture, we can use to compute for a large number of continuous message input. Like in the blockchain, this message can be billions, like 4 billions. And by compute for many continuous messages, they can generate one hash per one cycle. This is the reason that they can achieve high performance. But this architecture is very general, and I just consider it as a small contribution. Because in this architecture, in our group, is the first one proposed this architecture. The second one is the idea 2 and idea 3 is our main idea. Now before go to the idea 2 and idea 3, let we analyze the fully BLAKE accelerator. As you can see here is the message compression. This is two parts. First part is the message compression. This part occupies around 88% of error. A lot of studies are proposed to improve the message compression, and the second one is message permutation. It just occupies for 12% of error, and until now, no academic research is proposed to improve the message permutation. But in the blockchain mining, just only 10% error. More than 10% error is also very the big deal, because in the blockchain they have to consume a lot of power consumption. Reduced power is also the research trend today. So this is the reason that this is our research today. Now let's go to the message permutation. So message permutation has two components. The first one is register, used to store the message inputs here. So the IE2 name register optimization, and the second one is the permutation circuit. In this circuit, they just have a lot of short computation. This is the reason that in the idea 3 we propose the SHA optimization. Now let's go to the second one, the register optimization. Now as you can see here, this is the message input that we analyze the rates of work change in the continuous message. Messages. Now you can see here, this is the message input, and in each message input, it has 16 works here. As we analyze the rate of work changes. Now this you can see here in the normal application. Every works here have frequently changed works, because we don't know the value of this kind of message input here. Is frequent change in each message input. But in the blockchain mining, we know that they contain 3 groups. In group 1 is frequently changed words. Like they have to for like billion messages in this kind of words, they have to change continuously. And also they have some words is infrequently changed words. Like for example, like 4 billion times they can change for the time. This is the reason that take a lot of time and we change the value of this word. And the final one is the unchanged words. This means that for during the machine input, they never change before. Now, to better understanding my my idea 2, that we analyze the real application. So as you can see here, it is the message permutation. That we analyze the message input, what is the block header in the direct network, what is also the blockchain network, similar like the Bitcoin, but they use BLAKE for blockchain mining. Now, as you can see here in the message, in the block header, this data is the unchanged word. Unchanged words. So the value of unchanged words is 00 or 8001, like that. And in during blockchain mining, for example, like from the block header 0 to block header 1 million is also the same value, like that, like 00 or 8001. This is the reason that this is constant values we can remove, don't need to use it. And the second one is infrequently changed words. This like the H side time is extra data or stack version. For example, like in the block header 0, they are the same. But when you go to the block header 1, they just change all the data here. And when mining for the block header 2 is also changed, this means that they infrequently change when mining the data. So this is the reason that we, for during the mining task of one block header, this value are unchanged. This is the reason that we can remove it. We just keep for one register to store the message in the next block, header. And this here is the nonce value. They can have the frequently changed data during the blockchain mining for one block header. Now, as we see here, this is the proposed register structure in the direct blockchain mining. As you see here, I just try to reduce a lot of register. This is the example, the practical example of our idea tools in the real blockchain network. Now you can see in the general. The idea 2 is aimed to improve the error and power consumption. Now here is the normal register structure. They have to use enough register to store. This is the unknown data value. They have to use enough to store data. And the second one is the proposed register structure for blockchain mining. As you see here, just the block header and reduce a lot of register here. And the final one is the SHA optimization. This is the SHA optimization, like I just mentioned about the SHA computation in the message permutation. Now, as you can see here, in the permutation circuit 0, they have 16 the SHA gate. This is the 32-bit SHA gate or 64-bit SHA gate. And in LV permutation circuit, they have 16 like SHA gate, and like here, like 14 message permutation circuits, they have contain a lot of SHA gate. This is the reason that we can reduce it to improve the error. Now, we also analyze the message input, which is also the blockchain in the direct network, which is the real blockchain network. Now you see here in infrequently changed words or in frequently changed word. Maybe this is the infrequently changed word, but we don't know about the data. For example, like in the block 0 is different, block 1 different, block 2 different. We don't know about that. This is the reason that we have to keep this SHA gate to compute. It's unpredictable results. And the final one is on-chain value works. Like in this accelerator, they have 00 or 001. This is the reason that the result of this computation we can predict is the predictable results. We can replace it by the hardware. You see here, we just have no SHA gates at all. This is the reason that we can reduce the SHA gates. Now, let's go to the general architecture. So our ID2s aim to reduce the area and power consumption. Now you can see here, this is a normal permutation circuit for any application, and this is the proposed permutation circuit in the blockchain mining. By replace several SHA gates by hardwire, we can reduce the SHA gates. And reduce SHA gates, we can reduce error and also reduce the power consumption to improve to demonstrate the accuracy of our accelerator. We will implement it on the real FPGA, which is also the ABL FPGA here. This is our proposed accelerator. So it's not a very important part. So let's go to the next part to evaluate it. So as I mentioned, the ID1 is not the main, and ID2 and ID3 is the main idea. So this is the reason that the result one I will evaluate just only for the register and SHA gate optimization, just in the theoretical evaluation. Now, as you see here, I have to check for all of different numbers of contents and infrequently changed words, like from 1 to 15. And as you can see here in the register, this can optimize to 5.4 to 87.9% of the register optimization. I just want to note that it's just the optimization in the message computation is not for entire circuit. Like in a SHA gate, it can be like 6.5 to 93.8% of SHA optimization. Now let's demonstrate it in in the real hardware platform or on the ASIC. First, in the ASIC first, I already since I already implemented in the ASIC. Now as you can see here is the normal and proposed fully by BLAKE. First in the BLAKE 256. Now what is the normal? Normal here is just only the accelerator of the ID1. It just contain ID1, and in proposed is contain ID1, 2, and 3. Now how we check how the ideas 2 and 3 improve the performance and improve the error and power. As you can see here, when you check it, it can up to 11.4 optimization in error, and in power it's like 21.1% optimization in power, and when it's also like 13.1 optimization in error efficiency, and 27.1% optimization in energy. This here error efficiency, and here is the energy efficiency. And similar to the BLAKE 256, here I just analyzed the BLAKE 512, and also the result is also very good, like the BLAKE 512 in the error and power and error efficiency, and also energy efficiency. Now, in the next one, we compare that with the related works on FPGA. Now, first, let we evaluate it on the Vertex 5. as you can see here, by content the ID1, our accelerator can achieve 14.6 to 222 times better in throughput compared to the previous works. And when content the ID2 and ID3, our accelerator can achieve 1.3 to 4 times better in area efficiency. So the reason why I do not show you the power here, the power consumption, because the previous work doesn't give any power consumption here, and just only give it doesn't make sense. And also the next one is the vertex 6 FPGA. Similar to the vertex 5, our accelerator is also significant better in throughput and also significant better in area efficiency when compared to the previous works. Now, in the final one that we compare it with the most power CPU or GPU. Why I have to compare with the CPU or GPU here? The reason is the CPU or GPU is the main hardware platforms used to mine in the blockchain mining. And as I mentioned, for fair comparison, in this kind of CPU or GPU, I use the open source in the internet, really developed by the blockchain mining company for the running the BLAKE algorithm. So as you can see here, our accelerator is like more than 100 times better in power consumption, and also like 20 times to more than 20 times better in energy efficiency when compared to the CPU or GPU. And in here, this normal fully byte is mean like the fully byte with only the ID2, ID1, and here is the ID1, 2, 3. And when compared to it, our accelerator can 1.2 times better in power consumption and energy efficiency. 1.2 times here is similar to the 20%. So let's go to conclusion. We have proposed two accelerators, which is SHA-2 and BLAKE accelerators for decentralized networks. In the SHA-2 accelerator, we have proposed Multimode SHA-2 accelerator to achieve high performance and high hardware efficiency and high flexibility. Experimental results show that our accelerator is better than the FPGA-based works and also CPU or GPU in performance, hardware efficiency, and flexibility. And the final one is BLAKE accelerator. We have proposed a fully byte BLAKE accelerator with a compact message permutation. This means for ID2, 1, 2, 3 to achieve the high performance and also the energy efficiency. Experimental results show that our accelerator is better than FPGA-based works and CPU or GPU in performance and hardware efficiency. So I have like 1 minute to thumbs up. And around in the future works, I will be decide the accelerator can have higher flexibility. It means like they can cover for a lot of hard function. It's just not only in SHA-2 or BLAKE. And this is our publication. This is the journal papers, and the second one is the conference papers and the patent. So thank you everyone for listening.
So anyway, your proposed hardware architecture can reduce the power consumption as well as improve the throughput performance.
Yes.
And I'm not sure what is the main idea for reducing the power consumption. So the reducing the number of registers or the other good ideas, but I can't follow your presentation. So please explain.
Yes. So as I mentioned about that, let's open this. In this part, like when we reduce the register and the socket, we can reduce the area and make the circuit smaller. If smaller, they consume less power consumption. This means that when we reduce the area, we can reduce the power consumption.
You mean you reduce not only the number of registers, but also the error occurrence.
The register and the show up. This
Right, so
socket.
So your architecture seems very specific for
Yes.
the blockchain mining.
Yes.
And I wonder, in your architecture, how about the error occurrence? So I mean the very specific bit level architecture. So I'm not familiar with this area. So this specific architecture improves the transaction through the performance and reducing the power consumption. But how about the error or the incorrect something?
What is the error?
So the result is incorrect.
The result is
Yes. No error.
no error.
Or the reliability of the system.
Reliability.
Yes.
No problem about that. Yes.
Okay, so please show the slide 1, number 46. Yes, so here you finally show the comparison results of the CPU in comparison with the CPU and GPU.
Yes.
And so my feeling is normal fully pipeline FPGA, the performance is almost the same as
But it's right now it's not the same, but now as you can see here, the hash rate is not the same. It's smaller, but in this case, I just use for like a very small circuit. But in the blockchain mining, they can deploy or they use a lot of cores to increase it. As you can see here in the FPGA, our FPGA, I just use for several percentage of this FPGA. Like they consume for very just like 1 power. And here we can decide it into like 64 cores or like 100 cores to similar to the hash rate. But the idea here, I just want to show that the power consumption and energy efficiency. If, for example, like the power here, we just like 4 times. 4 times here is like 10 watt, and here we can like 4 times like hash rate here. Like it's also the same with the CPU here, because we just use 10 cores in the FPGA. Yes, when we divide it, it's also we lose the 10 here, 10 core here. This is the reason that we just only analyze in 1 core, and when we increase the large number of cores, it's also similar. It's not the same, but it's a little bit similar.
So you mean your proposed architecture outperforms the architecture of normal fully pipeline when the number of cores increase?
Yes.
Okay. Okay, so I have last one comment for your dissertation. In your presentation, first you showed some background, society 5.0, and how important your proposed architecture is for not only for blockchain mining, but also supporting serial computing science. But in the doctor thesis, no description is included. So I would like to ask you to include such a very important background to the introduction of your PhD thesis.
The description of society.
Right. Okay, so then I have some comments. So the dedicated hardware, special purpose hardware, should always be better than the general purpose CPU or GPU. So then I guess it's better to compare with not with the GPU, CPU, rather it's better to compare with the Intel special purpose CPU. Supported that support the SHA-256. So then how about to compare with the Intel chip?
So right now, because the Intel use, just very, very low technology, and in our lab, just you high technology like 64 nanometer, and Intel use the 9 nanometer or is smaller. But right now, I'm just like estimation or just normalize it, maybe. When just I implemented on the ASIC 64 or 65 nanometer, and I just try to normalize it into the same technology. But I'm not sure it's fair or not because we don't have the same technology. It's really, really difficult to compare like that.
So I believe you haven't received any sharp comments during your PhD. It's very boring. So let's make it a little bit interesting, right? So my comment will be very, very sharp. Okay, basically, I like your project. I like everything here, but I don't like this research and experiment at all. Because just following Kasahara-sensei's question, how can you improve the energy efficiency or something? The only idea in your circuit is to remove some unnecessary XOR gate or register and get some improvement. The only thing you can success because I don't know if it's success or not. You can better than your comparative work is that those designers have never noticed such a naive point, or they didn't do this at all. That means the only chance you success is nobody did this. Otherwise, you will lose everything. The only idea you put is just remove some unnecessary, very tiny circuit like XOR gate. So in this one, I would like to see more. If you write this in want to improve it a little bit, just make some future work or something like this. How to improve it, or how much room you have. By what? By summarizing what is a blockchain blockchain applications property. For example, in some calculation works like machine learning, we have the problem of data reuse. So if you reduce the data reuse, store and load something, you can reduce the power. And in some other applications, data movement is also important. In some other applications, of course, many different properties, then many different strategies. So in this case, you'd better think about the future, what kind of strategy you use. Because this one, to be very honest, blockchain research work is very complicated, but blockchain implementation is super simple from the viewpoint of circuit. Because no any data recall, just straightforward calculation, and the data is not so massive, just very light data, and parallelism is not so much. no massive data, just very straightforward. Receive some data and do very simple calculation, just throughput it. In such a case, how can we improve the efficiency, like energy efficiency? For example, in AI application, especially in CNN, convolutional neural network, we just want to reduce the total number of calculations. Then we can speed it up and we can reduce the power consumption. But in this world, you can never reduce the total number of calculations, right?
Yes.
And no any data recall, no any data reuse, something like this. So you have very tiny room to improve this kind of things. Just like Nakashima-sensei suggests, so why not compare to some specific hardware or something, or I don't know the mainstream, but I think blockchain system will be developed for open market users, not the closed market users. That means just another way may be better. How to improve the implementation by using the GPU or CPU, not your developed device, unless you can sell this device to every people on this planet. They use your device, then that's okay. But most of them will use GPU or CPU or something like this. That's all.
Thank you, Sensei.
Can I ask a question?
I think.
Please try to page 44. Just like Nakashima-sensei and Johnson said, you design a specific ASIC accelerator. Compared to GPU and CPU, you get a high performance, but compared with some other ASIC designs, you just compare this reference. I just saw that it's more than 7 years, even 10 years ago. So why don't you compare with some state-of-art ASIC design? I think so. Maybe in few years, some others can design some BLAKE accelerator. Why don't you compare with them? Look at this reference more than 7 years.
So I know that since I really want to know about the conversion between our accelerator with the ASIC. Yes, but right now I'm just the ASIC. The ASIC mining use the totally different architecture, like it use a lot of cores, but in our architecture just improve for one core, and when I compare to the blockchain, the ASIC miner is not fair right now. And actually, if I'm just mainly focused implementation on the FPGA, if you compare in the ASIC is also unfair right now, and maybe actually 100% our throughput will really smaller than the ASIC right now. And ASIC doesn't, the ASIC miner doesn't show any architecture and doesn't show anything about their, about the RTO or anything. I have nothing to compare with that.
So you mean that recently we do not have the related work in the BLAKE for you to compare it recent, right?
Yes.
So you compare with the 10 or 7 years ago result. That's what you mean?
Tensei want to know that why only yes, it's also the one thing, but Tensei also want to know that why I'm not trying to compare with the ASIC miner right now, because ASIC just like newly. That's why. And also like there is the FPGA-based work they have proposed for like 10 years, or like here is the 7 years, because also FPGA doesn't have any new works right now.
Yes, really. The BLAKE, there's a lot of companies they develop the ASIC circuit for BLAKE, but for business purpose, it's not for academic purpose.
You mean recent years there are no FPGA-based works for BLAKE?
Recent year, the companies try to implement the BLAKE in ASIC for blockchain mining, but this is the company. They didn't share any architecture or anything. They just show the result. We don't know how about this architecture for fair automation.
Academic papers shows the
This kind of reply is very dangerous in academia, from the viewpoint of academia, because some scientists will ask you when you can never find any papers during 10 years, then stop your research work. Never do this. Why? You gotta think about why. You are the smartest guy on this planet, other guys can never thought about this? No, never. Because they don't want to do this. I understand the situation, but please avoid to answer in such a way. Otherwise, some people will ask you sharper questions. Okay, thank you. I'm sorry.
So then the last question. So how long the lifetime of the algorithm? How long mean for example, the 2 years, the 3 years, you can keep the same algorithm in ASIC, or be discarded and the new algorithm will come?
It depends on when somebody can hack this algorithm, and the new algorithm will try to propose to replace this algorithm. Just like, for example, like SHA-1, they be hacked by someone, and then they try to propose the SHA-2, and right now there's no significant hacker try to hack this. This is the reason that the SHA-2 can work until now. And so the answer is depends on some person can hack it or not. It doesn't mean like for 5 years they propose a new one, or 10 years they propose a new one.
So then I mean if the lifetime is around 4 or 5 years, so then you cannot continue to build the ASIC. Okay, so then you can follow the algorithm. So but then after you fabricate the real chip, so they'll never use it. So because that's the old one. So then my last question is, what's the direction of your research? So that you can keep the special purpose hardware. So but you never get the commercial based systems.
Yes, as I mentioned in the future works, so like in the machine learning, they also have some mathematic. They can design some something for similar to to compute for this kind of mathematic. For example, like Sensei design for Emacs or IMAX for the machine learning, and in my architecture, like in the cryptography, they also have a little bit similar. It's not like the same similar. It's just like a little bit similar in the mathematics. Like it uses the SHA gate, only SHA gate, like multiplexer is no multiplexer, just no multiply like SHA gate adder. And in the future, I have to decide the architecture can compute for any cryptocurrency, for any cryptography. Like in the future, when someone try to propose a new hash function, and also my accelerator can configure for it, because like in the hash function, they also have to follow the rule to decide it. Like only SHA gate, like the adder, or just like that, or sheep, or just only several competition like that.
So as his discussion with me, that his final target is to develop like a general purpose accelerator for multiple kinds of hash algorithms. Yeah. So of course it should be better performance than the current CPU and GPUs, but it's for hash function, but several hash function, not only one, but several hash function. So to be able to design such case of efficient and general purpose accelerator, so he needs to master several kinds of hash algorithms. Therefore, he research one by one, and for each algorithm, so he research about that, understand about that, and then they have some, maybe not too big, but just some contribution. Is now in these two research about SHA-2 and BLAKE, he has some contribution, but it's actually this is not the final target. So the final target is based on this understand, and he will try to develop like general purpose actually for multiple hash function.
Okay. So then at the final defense, so you should summarize all of the questions and the answers, so then you can rewrite the thesis. So this is the first version.
Yes, that's it.
All right. Okay. So let's close the first defense.
Thank you so much.